Welcome all to the next session of problem solving of fundamentals of food process engineering. So in this week we'll be solving the syllabus problems related to the syllabus of week 4. So if you guys have any questions in between, you can stop me or put a message in the chat so that we can stop and discuss the doubts there. So moving on to question 1. Is the slide visible? Am I audible?
Yes, visible.
Okay. So question 1. The liquid food containing 13% total solids is concentrated to 38% solids in an evaporator. If the mass flow rate of the feed is 120 kg per hour, calculate the total amount of water evaporated in the process. So any clue how to solve this question? What are all the streams that are present in an evaporator? So what goes in, what comes out? So in an evaporator, if you see, you actually send in a dilute feed, let's say at the flow rate of F, and XF is the total fraction of solids that is present in the inlet feed. And once you feed in the dilute solution, you pass in steam through a separate tube. The steam and the feed are not mixed, they are in separate tubes. And from the heat transfer that is happening from the steam to the feed, there is evaporation of the liquid that is taking place, and you will have vapor flowing out with a mass flow rate of V, and then you get a concentrated product at a mass flow rate of say L. And since you are concentrating the solution, the total amount of solids that is present in the concentrate and the feed are not the same. So XP will always be higher than XF. That is, it will be a much more concentrated solution that you get out after evaporation. So the given that is there in the question is XF, that is total amount of solids in the feed is 0.13. The total amount of solids in the concentrated solution is 0.38. And the mass flow rate of the feed, that is F in here, is 120 kg per hour. So we have to calculate the total amount of water evaporated in the process, which is nothing but V here. V is the water that is evaporated in the process. So we need to find out V. So how do you proceed with this? Any idea how to proceed to find out V? So you do something called as a mass balance. So we have something called a total mass balance, where your inlet feed is the mass of the inlet feed is equal to the mass of the outlet feeds. So here we are not considering steam. As you can see here, we are taking F, which is the feed, is equal to L plus V, which is the product, concentrated product, and the vapor. Here we are not considering the steam because the steam and the feed are not mixing. The moment there is mixing of the steam, then you can say that you can add the flow rate of steam here as well. But since the steam is not mixing, we are concerned about only the feed flow rates and the outlet flow rates. So F is equal to L plus B. What are the other balances that you can do here is the total solids balance. Since only water is getting evaporated, the solids that is present, amount of solid that is present is the same in feed and product. Only the concentration is changing. So if like say 5 grams of solid is present in feed, same 5 grams of solid will be present in the product. Only thing is that the volume of the feed and the volume of the product will be different. So the concentration is also different. So if we do a mass balance for solids, we have F into XF. F into XF will give you the total amount of solids that is entering the evaporator. And since in an evaporation process, it is only the water that is getting evaporated and not the solids, your V, that is the vapor stream, will not have any solids. So that will be 0. Only the product stream will have the solids. So you will have L into XP. So the total amount of solids entering is the total amount of solids leaving. This is the mass balance for total amount of solids. So from this, can you calculate V? You have two equations. So how do you go about calculating V? You can either unmute yourself to answer or you can put it in the messages. Yeah?
First we have to find L and then substitute in total mass balance.
Yeah. So we don't know both L and V. So we're substituting the values in the mass balance for solids. So F is 120 kg per hour, XF is 0.13, L we don't know, and XP it is given that 0.38. So from this we are calculating L to be 41.05 kg per hour. So moving on, with this L we substitute back into the mass balance. We already know F. From there we will calculate V. So substituting L in the total mass balance equation, 120 is equal to 41.05 plus V. So you are getting V equal to 78.95 kg per hour. So the answer to this question is option C. Is this clear? Moving on to the next question. In a triple effect evaporator, the saturated steam is entering the first effect at 375 Kelvin and the boiling point of the solution in the last effect is 315 Kelvin. The overall heat transfer coefficient for the first, second and third effects are 2950 watt per meter square Kelvin, 2100 watt per meter square Kelvin and 1450 watt per meter square Kelvin respectively. So what is the boiling point of the liquid in the first and the second effect if boiling point rise is negligible and the heat transfer area is the same in all effects? So we'll deal with each sentence one by one. So what is a triple effect evaporator? Any clue what's a triple effect evaporator and how is it different from the figure that I showed you earlier? So in a triple effect evaporator, instead of having one single evaporator unit, you have multiple, in this case 3 units connected in series, which means that you are feeding your dilute liquid in one evaporator and each evaporator is known as the effect. This is the first effect, this is the second effect and this is the third effect. So you are feeding your dilute solution in the first effect and you are passing steam also in the first effect. So some amount of vapor or some amount of water will be evaporated, that will go as vapor, and that vapor is actually fed into the second effect and the concentrated liquid from the first effect is passed on to the second effect. So why we do this is because instead of using fresh steam every single time and wasting the amount of steam required, we actually reuse the vapor from the first effect so that lesser amount of steam is required and it is much more cost effective process. So the vapor from the first effect is fed into the second effect and the concentrated liquid from the first effect is also fed into the second effect. So now again an evaporation process takes place and again the vapor coming from the second is fed into the third and the concentrated liquid coming from the second is fed into the third. Finally, whatever vapor comes out is what is condensed for further purposes and whatever liquid, concentrated liquid coming out is your final product. This is in case of a triple effect evaporator, you have 3. So here you can see there are 3 different temperatures, T1, T2 and T3. This is because all of these are maintained in a different pressure. So this particular effect will be maintained at a higher pressure, this at a slightly lower and this at a much lower. So because the pressure is different in each of the effect, the temperature that is required to boil the liquid is also different. The temperature is directly proportional to the pressure, operating pressure in an evaporator. Lower the pressure, lower the boiling point of the liquid. So here, in the other effects, the pressure is actually lowered. So your boiling point in each of these effects is also lower. So actually T1 is greater than T2, greater than T3. Is this clear? Any doubts in this particular arrangement of the evaporators?
Why T1 is greater, ma'am?
So actually the effect here, the effect here is maintained at a higher pressure. Okay, let's say the pressure here is P1, pressure here is P2, pressure here is P3. We are maintaining it in such a way that P1 is greater than P2, P2 is greater than P3. This is maintained because generally fluid flows from a higher pressure to lower pressure. So like say if I open a valve here, my liquid will automatically flow from a higher pressure to a lower pressure into the second effect. But say if I don't maintain this at a lower pressure, if I don't maintain the subsequent effects in a lower pressure, then my liquid will actually flow from a lower pressure to higher pressure. For that I need to add pumps that will just increase the cost of my production. So to decrease the cost of the production and to help the liquid to automatically flow from one effect to the other effect, pressure 1 is greater than pressure 2, pressure 2 is greater than pressure 3. And generally liquid's boiling point is directly proportional to the pressure. So your boiling point in first effect will be higher, in second effect will be lower than 1, and third effect will be lower than 2. Is this clear?
Yes, ma'am.
Okay, so even in the options you can see that your T1 here, T3 here is given, that is the boiling point in the last effect 315 Kelvin is given. So your T2 should be higher than 315 and T1 should be higher than the T2 value. That is how it should be. So given here, let's look at the given. So the saturated steam temperature is given, which is 375 Kelvin. So this Ts that is fed into the first effect, a temperature is given as 375 Kelvin. And the boiling point in the last effect is 315. That is T3 is given as 315 Kelvin. The overall heat transfer coefficients in each of the effect is given. Say U1 is 2950, U2 is 2100 and U3 is 1450. So since your temperatures are not the same in any of the effects, the amount of heat that requires to boil the liquid will also be different. So your U1, U2, U3 will also be different. So generally a heat transfer process, heat transfer can be expressed as Q is equal to U, which is the overall heat transfer coefficient, A, which is the area of the heat transfer, and delta T, which is the temperature of the steam minus temperature of your liquid. That is the temperature that difference that is required to enable the boiling of the liquid. So delta T will always be the temperature of the inlet steam minus temperature of your operating effect or the boiling point here. So Q is equal to UA into delta T. So how we find the temperature at each of the effects is by a certain derivation that I will explain you right here. So let's consider this as equation 2.1. So if you look at the total delta T in the entire process, all three effects included, that will be your Ts, that is the temperature of the first inlet steam in the first effect minus the boiling point in the last effect. We actually calculate this by calculating the delta T at each and every effect. So delta T is actually equal to delta T1 plus delta T2 plus delta T3. So in delta T1, the first effect, the delta T is actually equal to Ts minus T1, that is the inlet steam minus the temperature at that effect. And for the second effect, it is the temperature of the vapor that is entering to heat the steam, that is T1 minus T2, plus for the third effect it is T2 minus T3. Is this clear? So this is the delta T of the total process, delta T1 plus delta T2 plus delta T3. So if we consider from equation 2.1, if we consider that the area and heat transfer rate are the same, so since Q is equal to U into A into delta T will be Q by A 1 by U1 plus 1 by U2 plus 1 by U3. But I'm considering all the all the three effects. Is this understandable? Had it been only one effect, we will have Q by A by U1. If it was only the second effect, we will have Q by A by U2. Since we are considering the entire for all the three effects, we will have an addition of all the overall heat transfer coefficients, Q by A into 1 by U1 plus 1 by U2 plus 1 by U3. So if this was the first effect, you will have Q by A is equal to U1 into delta T1. So we substitute Q by A, since we assume that the heat transfer rate and the area for all the three evaporators are the same, we substitute Q by A back into this equation. So you will have U1 delta T1 into 1 by U1 plus 1 by U2 plus 1 by U3 equal to delta T. That is, we are substituting U1 delta T1 back in this equation. So if we rearrange this, you will have delta T1 equal to delta T into 1 by U1, the whole divided by 1 by U1 plus 1 by U2 plus 1 by U3. This is derivation clear? So
Yes,
basically
ma'am.
it means that if you know your inlet steam temperature and your final temperature, that is the temperature in the last effect, and you know the overall heat transfer coefficients, you can find out the delta T in each of the effects. So this is for delta T1. So if you have to find for delta T2, the only thing that will change here is U2. So instead of 1 by U1, you will have 1 by U2 and the denominator will be the same. Same way you can find for delta T3 as well. So this is a pretty generalized equation where for each effect you can find out the temperature difference and hence finally the actual boiling point at that effect. So using this equation, we'll calculate delta T1. For that, first we need delta T. Delta T is nothing but Ts minus T3. Ts is given as 375 Kelvin and T3 is given as 315 Kelvin. So this is 375 Kelvin minus 315 Kelvin, which is equal to 60 Kelvin. So now we are substituting back delta T in the equation. Delta T1 is equal to 60 into 1 by U1 divided by 1 by U1 plus 1 by U2 plus 1 by U3. These are the values that are given in the question. So from this equation, you can calculate delta T1. Is this clear?
Yes, ma'am.
Okay, similarly, you can calculate delta T2 as well. Delta T2 is equal to 60 into, that is delta T into 1 by U2, the whole divided by 1 by U1 plus 1 by U2 plus 1 by U3. So similarly, you can calculate delta T2, which comes out to be 18.987 Kelvin. But what is asked in the question is the boiling point at that effect, not the temperature difference. So with delta T1 and delta T2, you need to calculate what is T1 and T2. So what is delta T1 in the first effect? What is it? How do you calculate the temperature difference?
Ts minus T1.
Yeah, so delta T1 is Ts minus T1, whereas in case of delta T2, since the vapor from the first effect is actually acting as the steam, so that will have the temperature of T1. So here it should be actually T1 minus T2. Sorry. So T1 is 375 Kelvin minus 13.52 will give me T1, which comes out to be 361.48 Kelvin. And T2 should be actually T1 minus T2. So T1 you got here, substituting the T1 value minus 18.987, which is calculated from delta T2. So with that you can calculate T2, which turns out to be 342.49 Kelvin. So as you can see here, your T1 is greater than T2, T2 is greater than T3. This is how it will, this is because you're maintaining pressure differentially in each of the effects to enable flow from a higher pressure to a lower pressure. So the answer to this question is option D. So with temperature in the last effect and inlet temperature and the overall heat transfer coefficients, it is possible to calculate the temperature in each of the effects. Moving on to question 3. Statement 1. Reducing the operating pressure decreases the delta T. Statement 2. Preheating the feed can reduce the area of heat transfer and thus the size of the evaporator. So which one of these statements are true and which one of these are false? What about the second statement? Any other answers? Okay, so statement 1, reducing the pressure reduces the boiling point or the operating temperature of the evaporator. But here, say if you reduce the pressure, let's say the evaporator is operating at a temperature of T1. So if you reduce the pressure, T1 reduces. But here we are talking about delta T, not the T1. Delta T is actually equal to Ts minus T1. So if you reduce the pressure, you are reducing T1, and let's say your steam temperature is kept the same. So if you reduce T1, your delta T actually increases. So reducing the pressure, operating pressure, does not decrease the delta T, it increases the delta T. Okay, so you need to be careful whether we're talking about the operating temperature or the delta T here. So statement 1 is false. Moving on to statement 2, if you preheat the feed, the amount of time or the area that is required to contact with the steam actually reduces. If you're already heating up the feed, it is going to be much easier to heat it to its boiling point inside the evaporator. So the amount of time and the amount of contact that it requires with the steam drastically reduces. If you do not require that much contact with the steam, you can happily reduce the area of the heat transfer and to achieve the same amount of evaporation. So if you reduce the area of the heat transfer, you can build a much smaller evaporator and hence the cost of the evaporator also goes down. So are these two statements clear? Any doubts? So the answer to this question is option B. Moving on to question 4. The straight lines obtained between the boiling point of a pure solvent and boiling point of a solution for different concentrations of a solute is called During lines, Fourier lines, isobars, or boiling point elevation. Any answer to this question? Okay, so a During's plot is actually a plot that is used to find out the boiling point elevation of a solution at a particular solute concentration. So basically, a water has a lower boiling point than a sugar solution. So if you add a solute to a solvent, the boiling point actually increases. And During's plot is based on the concept that the boiling point of the solution is directly proportional to the boiling point of the solvent. That is, in case of uh, our interest, the solvent is actually water. So the boiling point of solution is always proportional to the boiling point of the water. And higher the solute concentration, higher is the boiling point of a solution. So if you actually plot this relation, so this is what a During's plot looks like. So you will have boiling point of your solvent here and a boiling point of your solution here. And you will have multiple lines, each for a different concentration of the solute. So, and we have multiple graphs for each kind of solute. You have for NaOH, you have for NaCl. For different kinds of solute, you have different kinds of graphs. Each of them will tell you the relation between the boiling point of the solvent and the boiling point of the solution. So each of these lines are called During's lines. So this particular graph is for NaCl. So when we're talking about evaporation here, as in when you evaporate, the concentration of your solute actually keeps increasing inside the evaporator. So your boiling point that was at time t equal to 0 will not be the same as some say t equal to 1 hour, because now your solution would have already concentrated a little bit. That would have changed the solute concentration in the liquid, and hence your boiling point would have actually increased. So while designing the evaporator, you need to understand this concept of boiling point elevation, and you have to design the evaporator in such a way that you're operating the evaporator including all these elevations that are possible. So this phenomenon is called boiling point elevation, but this is captured as a relation between boiling point of solvent and boiling point of solution in the During's plot. So the answer to this question is option A. Is this clear? Moving on to the next question. Which of the following evaporators are used for highly viscous food products like say tomato puree? You have a climbing film evaporator, you have falling film evaporators, you have jacketed open kettle evaporators, and plate type evaporators. So what is a problem when it comes to highly viscous foods? What is the most common problem that we face when we are dealing with highly viscous fluids? So what happens when you heat an already viscous food product? Yeah, the answer is C, but what is the logic behind it? So when you heat a highly viscous product, your water content in the product starts evaporating. So this will result in a more concentration of the product. So what was already viscous will actually become more viscous due to heating. Sorry. So what was once a viscous product, because of concentration in an evaporator, it will lead to much more increase in viscosity. So the moment it is becomes highly viscous and thick to flow, the heat transfer becomes very difficult. So in order to enable the heat transfer, we are providing with agitators inside the evaporator. So there will be some kind of a stirrer mechanism or an agitator mechanism that will constantly stir the viscous fluid as and when it gets evaporated. So because of this stirring, it will increase the heat transfer coefficient and hence the heat transfer rate as well. So this agitator is only present in a jacketed open kettle evaporator. The rest of these evaporators, these film evaporators and plate type evaporators, all of these are more of a tube kind of an evaporator. So you will have either liquid falling and because of that it gets in contact with the steam and gets evaporated, or it will boil at the bottom of the evaporator and rise up, which is in the climbing film evaporator. On a plate type evaporator, you will have your steam and your feed being separated by a plate. So none of these have a capacity to have an agitator inside it. Only the jacketed open kettle evaporator will have a stirrer or an agitator, and you will have steam supplied at the outside, which will heat up the liquid, and then you will collect the vapor outside and the concentrated product from the down. So only this jacketed open kettle evaporator can hold a stirring system to enable heat transfer for viscous fluid. So the answer to this question is option C. Okay, moving on to question 6. In a single effect evaporator, the boiling film coefficient inside the tube is 1500 watt per meter square Kelvin. The steam condensation film outside the tube is 7000 watt per meter square Kelvin. So there are a total of 20 vertical tubes, 18 millimeter and 20 millimeter inside and outside diameter, and a 5 meter length, and a 15 degrees Celsius temperature difference is maintained across the tube walls. The thermal conductivity is 15 watt per meter Kelvin. The latent heat of vaporization of water is 2350 kilojoule per kg. Assuming no boiling point rise, no heat loss, and that the feed enters the evaporator at the boiling point, calculate the steam requirement in kg per hour. So, for any heat transfer process, the heat flux Q is directly proportional to delta T by R. So note here, this is small q that I am using. Small q actually stands for heat flux, which is equal to the heat transfer rate capital Q divided by area. So here, which is why we don't have an area term here. So heat flux is actually equal to Q by A, and that is directly proportional to delta T by R. So higher the temperature gradient, more is the heat flux, and higher the resistance, less is the heat flux. So for a convection process, the heat flux is equal to H into delta T. So H stands for the convective heat transfer coefficient, and delta T stands for the thermal temperature gradient. So if we rearrange this equation here, you have a small q which is equal to capital Q by A, where capital Q stands for the rate, heat transfer rate, and A stands for area, and you have delta T divided by 1 by H. So this form is very similar to the form in this equation here. So you can actually consider 1 by H as the resistance to the convective process. Hence, we consider here 1 by H as the resistance for convection. In contrast, for a conduction, your heat flux is equal to K, which is the thermal conductivity, delta T, which is your again temperature gradient, and X is the thickness of the material through which conduction is happening. So if you rearrange this, again you get delta T divided by X by K, where X by K will now act as similar to R, that is the resistance in the conduction process, where X is thickness of the material through which conduction is happening. So given that this is a single evaporator, why do we have three different heat transfer coefficient is what I'll be explaining now. So when you consider a fluid flowing through a pipe, let's say you have the cold fluid or your feed in the inside of the pipe, and you have steam in the outside of your pipe. So for the heat to be transferred from the steam into the feed, it has to undergo three different processes. First process is the convection process, where heat from the bulk of the steam should be transferred onto the top layer of your pipe. So there's actually, when a fluid is flowing or when convection is happening, there's a small film-like layer formed, and actually the heat transfer happens in this film. So that is, the temperature gradient occurs in this film-like region. So your first convection process is the transfer of heat from the bulk of the steam into the top layer of your pipe. So this is the resistance. This heat transfer is actually resisted due to the outer film, that is the outer film that is shown here. So first is the convection process, second is the conduction process, where heat has to transfer through the pipe wall. Let's ignore the fouling layers here. This is only if your material gets deposited and starts forming scales or layers. This will impede heat transfer, but we are not concerned about this right now. So from the outer of the pipe, it will conduct through the pipe into the inner layer. So this is the second process. This conduction is the second process, where your heat is transferred from the outside of the pipe to the inside of the pipe. So there is also resistance in this process as well. So this corresponds to the resistance due to conduction. And the third process is also convection, where heat is transferred from the innermost layer of the pipe into the bulk fluid of the feed. So, the heat is transferred from the innermost pipe after conduction to the bulk of the fluid, and again this also forms a film. Since we are dealing with convection here, this also forms a film, and uh, actual heat transfer happens in this film majorly. So the resistance due to inner film is also considered. So you can actually give this an electrical analogy where your different processes are connected in series, and the resistance is equal to the sum of all the resistance. So your total resistance of this entire thermal process is equal to resistance due to outer film, that is the outer convection region from the steam to the outer pipe, resistance due to conduction, that is within the pipe wall, and resistance due to inner film, that is from the pipe wall into the cold inner fluid. So the summation of all these resistances is actually the total resistance of this entire process that we're dealing with right now. So for the entire thermal process, you can actually write it as Q is equal to U into delta T. That is, heat flux is equal to U, which is the overall heat transfer coefficient, and delta T is the temperature difference. So this U will actually contain all the processes, the two convections and the conduction process into consideration, which is why in all these previous problems we've been dealing with the entire overall heat transfer coefficient that includes all of this. The moment you have separate heat transfer coefficients given for each of these processes, you need to add them up, calculate U, and then proceed with the problem. So if you rearrange this equation, you will have Q is equal to delta T divided by 1 by U. So for an overall process, 1 by U acts as the total resistance. So since the summation of all the resistances is equal to the total resistance, 1 by U is equal to 1 by H naught. That is, as we saw in the previous slide, 1 by H corresponds to the resistance due to convection, and X by K corresponds to the resistance due to conduction. So for resistance due to outer film, 1 by H naught is the resistance, and for resistance due to conduction, X by K is the resistance, and resistance due to inner film, 1 by Hi is the resistance. We are having two separate 1 by H because the heat transfer coefficient outside the pipe and inside the pipe are not the same. So you have two separate resistances for these. So 1 by H naught for outer film, X by K for conduction, 1 by Hi for the inner film. So we have all these values, but we need to find X, which is the thickness of the tube. So thickness of the tube can be calculated as R0 minus Ri, which is equal to 0.02 millimeter minus 0.018 millimeter equal to 0.002 millimeters. So it's actually D0 minus Di because you're dealing with an annular ring. So both the sides you have hot fluid. So you will be dealing with R0 minus Ri here also and R0 minus Ri here also. So it's actually effectively D0 minus Di. So you have 0.02 millimeter minus 0.018 millimeter, which is equal to 0.002 millimeters. So 1 by U is now equal to 1 by 7000, 0.02 by 15, and 1 by 1500, where H0 is 7000, Hi is 1500, K is given as 15 watt per meter Kelvin. So from this you can calculate U, which turns out to be U equal to 1060.6 watt per meter square Kelvin. So the area of heat transfer, you don't have the heat transfer occurring in the cross-sectional area. The heat transfer is occurring in the curved surface area. So the curved surface area is equal to 2 pi R0 into L. If you substitute the values, you have 2 pi R0 is nothing but 0.01 millimeter into 5 for the length of the tube, and we're considering into 20 because we have to calculate the area of all the tubes together. So the curved surface area is actually equal to 2 pi R0 into L into number of tubes, which is 20 in this case. So the total area of heat transfer for all the 20 tubes is 2 pi RL into 20, which equals 6.283 meters square. So now we have the area, we have U, we have delta T as well. So with that we can find capital Q. So capital Q is equal to UA delta T, which is also equal to S lambda. So what is S lambda? S is the amount of steam that you are sending inside the evaporator. That is the flow rate of the steam sending inside the evaporator. And lambda is the latent heat of vaporization. So whatever latent heat of vaporization the steam has, that is what is transferred to your feed to heat up the liquid, to heat up the feed. So the total amount of heat transferred is equal to S into lambda, that is the heat from the steam, which is also equal to UA into delta T. So we have lambda given, which is 2350 kilojoule per kg, that we are converting into joules by multiplying it into 1000. And we have U, which is 1060.6 watt per meter square Kelvin. A is 6.283 meter square, and 15 degrees Celsius is the temperature difference that is maintained and is also given in the question. So S from here we can calculate to be 0.0425 kg per second, and when you convert it into hours, it comes out to be 153.15 kg per hour. So the correct answer to this question is option D. Moving on to question 7. In a single effect evaporator, 125 kg per hour feed is entering at the boiling point of 50 degrees Celsius and is concentrated from 10 to 35%. The saturated steam is entering at 375 Kelvin. The latent heat of vaporization at 375 Kelvin is 2150 kilojoule per kg. The specific enthalpy of the saturated vapor at 323 Kelvin is 2250 kilojoule per kg. The heat capacity of the feed and the concentrated steam is 3.7 and 3.6 kilojoule per kg degree Celsius respectively. The overall heat transfer coefficient is given 1650 watt per meter square degree Celsius. We need to find out the heat transfer area. So any idea on how to proceed with this? Generally, when you have all inlet steam flow rates and the temperatures given, you will resort to the mass balance that we did in the previous questions. And in addition to that, since we have all the enthalpies also given, we'll do an energy balance as well. So considering this as the evaporator, you have F is equal to 125 kg per hour, which is the inlet mass flow rate of the feed. We have T1 given as 50 degrees Celsius. When converted into Kelvin, this is 323 Kelvin. And XF, that is the fraction of the total solids present in the feed, is 0.1, which is 10%. And in the concentrated product, it is 0.35. And the latent heat of vaporization at 375 Kelvin, which is also the temperature of the steam entering, is 2150 kilojoule per kg. And it is given that the enthalpy of the saturated vapor, that is the vapor that is getting evaporated, that enthalpy is 2250 kilojoule per kg. Remember that enthalpy should be at the boiling point of the evaporator. We calculated the boiling point as 323 Kelvin. So the enthalpy of the vapor that you should be considering is also at T1, which is at 323 Kelvin, and it is given as 2250 kilojoule per kg. So CPF, that is the heat capacity of the feed and the concentrated steam, is given as CPF and CPL, which is 3.7 and 3.6. This difference is because you have a more concentrated solution at this point at your product end. So because of that, the amount of heat required to raise the temperature by 1 degree Celsius, that is the heat capacity, also changes. So you will have different heat capacity for the feed and the outlet concentrate, and you also have the overall heat transfer coefficient given. So we'll start with mass balance and enthalpy balance. So the total mass balance is equal to F into V plus L. We'll consider this as equation 7.1. So what is the mass balance of the solids? So if you want to consider only the total solids that are present, the mass balance can be given by F into XF. This will give you the total amount of solids in the feed, and L into XP. This will give you a total amount of solids in the product stream. And since there is no solids transferred in the vapor, the amount of fraction in the vapor stream will be 0, which is why we are not writing it here. So this is, let's say this is equation 7.2. These are the mass balances. Now we move on to energy balance. So in the energy balance, since energy is transferred from the steam into your feed, you will actually consider the energy of the steam as well. So what is inlet in this case? Inlet, you have two inlets here. You will have a feed inlet and you will have a steam inlet. And you will have three outlets here. One is the vapor, one is the product, and one is the condensed steam. So what you need to understand here is that the temperature in which the steam is given is also the temperature in which the steam is taken out. So here it is given in as vapor and here it is taken out as condensate. So if it is entering at 375 Kelvin, it is also leaving at 375 Kelvin. Then what is being transferred is actually the latent heat of vaporization. It is the latent heat of vaporization that is transferred from the steam into the feed. So the temperature from the inlet and outlet steam will actually be the same. It is only the latent heat of vaporization that is being transferred. So energy balance is S into latent heat of vaporization. That is the heat that is transferred into the evaporator, S into lambda, plus F into Cp into Tf minus 273. So in all the energy balances, we'll consider the reference temperature as 273 Kelvin. In all of your energy balances, 273 Kelvin will be your reference temperature. So you have inlet steam and you have inlet feed also. The enthalpy of the inlet feed can be calculated as F, that is the mass flow rate of the feed, into Cpf into delta T, which is Tf minus 273. This is your inlet enthalpy. So the outlet energy balance can be given as your product stream will also have a certain enthalpy. So L into Cpl into delta T. Here your T will be your T1. That is, since your liquid is boiling at T1, that will be the temperature of your outlet steam, outlet concentrated stream. So T1 minus 273 plus your vapor will have the amount of vapor into enthalpy of the vapor. Since we don't have specific heat capacity of the vapor that is possible, we directly have the enthalpy of the vapor here. So inlet steam plus inlet feed is equal to outlet concentrate plus outlet vapor. So this is your energy balance. So we have all the values for this. We have equation 7.2 to obtain L. We have F, XF and XP. From there we will calculate L. So L is 125 into 0.1 divided by 0.35. So this will give you the mass flow rate of your concentrated product, which is 35.714 kg per hour. So from L we can calculate V. V will calculate using equation 7.1, which is your total mass balance. This is similar to your first problem that we solved. So V is F minus L. You will have 125 kg per hour minus 35.714 kg per hour. This will give you 89.286 kg per hour. So now you know the mass flow rate of F, L as well as V. So when you substitute all these inside your energy balance equation, you will get the steam requirement. So S into 2150, which is your latent heat of vaporization. So since all these mass flow rates are given in kg per hour, you need to convert it into SI units, that is kg per second. So 125 divided by 60 into Cpf into Tf, which is your inlet feed temperature, 323 Kelvin minus 273 Kelvin, equal to your L, the mass flow rate of L is 35.714 divided by 60 to convert it into kg per second, into 3.6, which is your specific heat transfer, specific enthalpy of the concentrate, into T1 minus 273. So here you can notice Tf and T1 are same. This is because in the question itself it was mentioned that the feed is entering at the boiling point. So only when that is mentioned, your Tf and T1 is the same, or else there will be a separate Tf, there will be a separate T1. So 323 minus 273 plus you have your flow rate of the vapor, which is 89.286 divided by 60, and the enthalpy of the outlet vapor is also given. So from this energy balance, you can calculate the S, which turns out to be 0.02379 kg per second. Till this, is it clear? So whenever you get all these enthalpy and flow rates, the first three things that you need to do is a total mass balance, the mass balance of the solids, and the energy balance. So from there, you can calculate the mass flow rates of each and every stream. From there, you can calculate the enthalpy and all if required, and the heat transfer rate as well. So now you know S is equal to 0.02379 kg per second. So as we mentioned in the earlier problem, the total amount of heat transfer rate is equal to the heat transferred from the steam, that is S into lambda. Q is equal to S into lambda. So you have S into lambda here, S here, and lambda is also given. From there you can calculate the total heat transfer rate. So Q is equal to 0.02379 kg per second into 2150, which is the latent heat of vaporization. So you have Q is equal to 51.1485 kilojoules. So again, one more relation we know, Q is equal to UA into delta T. So from this, you can calculate area. You already know U, you already know the delta T. You can calculate the area. So area is equal to Q, which is 51.1485. U is given 1650 watt per meter square Kelvin, and delta T here is the temperature of the steam minus temperature of the feed, or the boiling point temperature rather. So Ts minus T1 will be your delta T in this equation always. So 375 Kelvin minus 323 Kelvin. From this you can get area as 0.596 meter square. So the answer to this question is option A. Is the steps clear? The procedure or the logic behind solving is clear? Any doubts? Okay, so let's say instead of enthalpy of latent heat of vaporization, the enthalpy of the inlet and the outlet's steam is given. So in that case, you have to find out the latent heat of vaporization. So latent heat of vaporization will be the enthalpy of the steam entering minus enthalpy of the steam that is leaving. So since both of them are at the same temperature, the difference in the enthalpy will give you that extra latent heat of vaporization. So in case if only the inlet and outlet's enthalpy is given, we can calculate lambda, or the latent heat of vaporization, through this, and then you can substitute this in the energy balance and calculate S and then area. Moving on to question 8. This is a similar question, except that you will have to calculate the steam economy here. So in a single effect evaporator, 0.5 kg per second feed is entered at a boiling point of 55 degrees Celsius, and it is concentrated from 15 to 45%. Saturated steam Ts is entering at 375 Kelvin. The latent heat of vaporization at 375 Kelvin is 2050 kilojoule per kg, and the specific enthalpy of the saturated vapor that is leaving the evaporator is 2250 kilojoule per kg. The heat capacity of the feed and the concentrated stream are given, which is 3.2 and 3 kilojoule per kg degree Celsius. The overall heat transfer coefficient is 1550. We need to calculate the steam economy. So how do you proceed with this? So you again have all the givens, which is F 0.5 kg per second, T1 which is 55 degrees Celsius plus 273, that is 328 Kelvin, except that is the solids in the feed is 0.15, solids in the product is 0.45, latent heat of vaporization is lambda, which is 2050, your enthalpy of the outlet vapor is given 2250, CPF is given, and CPL, that is the heat capacity of the feed and the concentrated stream, are given. and your heat transfer coefficient is given. So again we'll go for a total mass balance, which is equal to F into V plus L. Inlet stream is equal to the sum of outlet streams, and you have the mass balance of the solids as well. F into XF is equal to L into XP. And you have the energy balance. So these will all be the same throughout your problem solving. S into lambda, which is your energy from the inlet stream, and F into CPF into delta T will be the enthalpy from your inlet feed. This is from the energy from your outlet concentrated feed, and VHV will give you the energy of the outlet vapor. So inlet steam, inlet feed is equal to outlet concentrate plus outlet vapor. So again you can calculate L from equation 8.2, which is 0.5 into 0.15 divided by 0.35. We are getting as 0.166 kg per second. So this you will substitute again in your energy balance equation to calculate S. You also can find out V from your total mass balance equation, which is equal to F minus L, that we are getting as 0.33 kg per hour. Sorry, kg per second here. Sorry. So when you substitute back in equation 8.3, you will get S is equal to 0.3359 kg per second. So S into lambda, which is 2150, your F 0.5 kg per second, Cp 3.2 kilojoule per kg degree Celsius, and Tf minus 273. Since it's already entering at boiling point, this will Tf and T1 will be the same. 323 minus 273. Your L, which is 0.166 kg per second, into 3, which is your CPL, into delta T, 323 minus 273, plus your vapor flow rate, 0.33 kg per second here, and then 2250 is your enthalpy of the outlet vapor. So from there you can calculate S is equal to 0.3359 kg per second. So steam economy is actually calculated by the amount of vapor that you generate in an evaporator divided by how much amount of steam that you give inside the evaporator. So your steam economy is always calculated by V divided by S. So we know the flow rate of vapor, which is 0.33 kg per second. We know the flow rate of the steam as well, that we calculated 0.3359. So from there you can calculate the steam economy, which is 0.99. So the answer to this question is option D. So the steam economy can actually go above 1 when you're dealing with multiple effect evaporators, where vapor of one effect is fed into the other effect. The total amount of vapor that is generated is actually much more. So in a multiple effect evaporator, you will have V1 plus V2 plus V3. You will have multiple vapors coming out, and the total V will be equal to V1 plus V2 plus V3. And your steam will always be lesser than the total amount of vapor that you generate. And this is only in case of multiple effect evaporators. So in a multiple effect evaporators, your V will be greater than S. So in that case, your steam economy can be greater than 1. So it is possible for steam economy to be greater than 1. And that is only in the case of multiple effect evaporators. Is this clear? So last question. Statement 1. The scraped surface evaporators are mainly used for low viscous foods. And statement 2. In an agitated film evaporator, agitator is provided to increase the heat transfer coefficient. So which of these statements are true or false? Okay, statement 2 is true. What about statement 1? Okay, the correct answer to this question is actually option A. So when you look at, this is an example of a scraped surface evaporator. So you'll have something like a stirring rod that is present, and you'll have a blade here. So this scraper blades will actually scrape out whatever is sticking to the walls of the evaporator. So when you're dealing with highly viscous foods or foods that require crystallization, that is that they form crystals upon heating. So when certain foods form crystals upon heating or they stick to the walls, you need something to scrape off the sticking parts, or else it will just accumulate and it will start getting contaminated by microbes. You will have to clean the evaporator properly. So all these can be reduced by involving a scraped surface evaporators. The scraped surface evaporators will have scraper blades to remove everything that is sticking onto the walls. So when you're dealing with viscous foods or fluids, as and when you concentrate, the amount of things that are sticking onto the evaporator will also increase. So scraped surface evaporators are generally preferred for high viscous fluids that stick to the walls, so that you can scrape out whatever is sticking. So hence statement 1 is false. It is used for high viscous fluids. And statement 2, as we mentioned in the previous questions itself, agitators are used in case of high viscous fluids to stir it properly and enable heat transfer. This is enabled by increasing heat transfer coefficient. Hence, statement 2 is true. So the correct answer to this question is option A. So that's all we have for this session. I'm sorry it went a bit long, but in case, I know this is a lot to deal with because there are multiple equations and other concepts that are involved. In case you guys have any doubt, you can either mail me or put it in the discussion forum. We'll reply back to you. I will make the necessary changes or the mistakes that were there in the presentation, and I'll upload it in the Google Drive, which will be accessible to you pretty soon. If you guys have any doubts regarding assignment 3 also, you can let me know. Okay, that's all for the session. Thank you. So I also wanted to discuss so I also wanted to discuss one of the questions that was arising in the previous week. So this was one of the doubts that was present in the previous session. So I'll just discuss this once. So the number of microbial count doubles in 6 hours. So how many times the microorganism is expected to grow in 10 hours? So you have multiple options given here. What you need to understand is that both microbial growth and death kinetics generally follow first order reactions. So the derivation of this particular equation is already there in question 1. If you guys want to know, you can visit question 1 again. So only in case of death kinetics are we seeing a decrease in the number of microbes. And because of this decrease in the number of microbes, you have a negative sign here. If you are dealing with growth kinetics, there will be a positive sign here. So for growth kinetics, it is ln n by n naught is equal to kt. Had it been death kinetics, you will have ln n by n naught equal to minus kt. But since we are looking at microbial growth here, we'll keep it as plus kt itself. So n is the number of viable cells at some time t, and n naught is the number of viable cells that is present in the initial condition, and k is the rate constant of the microbial growth, and t is the time. So here it is given that microbial count doubles in 6 hours. So n will be equal to 2 times n naught is what is given here. So n is equal to 2 times n naught, and n naught is already given. Since we don't know the actual value of n naught, and it is not required in this question as well. So we'll have n is equal to 2 times n naught, and n naught will keep it as n naught itself. So in the numerator and denominator, you will cancel n naught. So n naught gets cancelled, and you will only have ln 2 in the LHS. And since this doubling happens at time t equal to 6 hours, you will substitute t is equal to 6 here. So your equation will become ln 2 is equal to k into 6. So from this you can calculate k as 0.116 R inverse. And this k will substitute back in this particular equation and substitute time is equal to 10 hours that is required for the question, and from there we'll calculate the n by n naught. So k we'll substitute back as 0.115 or 0.116 r inverse into 10 hours, which is your total time. That will give you ln n by n naught. So if you take an antilog, n by n naught is actually equal to e power 0.115 into 10, which will give you 3.16. If you take an antilog of this RHS, you will get 3.16, which is equal to n by n naught. This will give you the number of folds, or how much times the microbe count has actually now increased. So n naught will be your initial count and n will be your final count. This ratio will give me the number of folds or the number of times in which the microbe has replicated. So the answer to this question will be n by n naught equal to 3.16, which is option D here.